My name is Ian Villa. I'm Uber Elevate's vehicle partner and strategic modeling lead. And as Mark mentioned, it's really important to understand Uber Air from a network perspective. So today, I'm excited to be able to share with you how we're looking at this by simulating fleets of electric vertical takeoff and landing aircraft in order to ensure that we can reach network efficiency. And it's important that we maximize efficiency when we launch and as we scale. The visualizations you see here are the notional growth of our markets in Los Angeles and Dallas-Fort Worth. And in it, you see exactly what we embody, or they embody what we aim to achieve using our simulation framework. Understanding traffic patterns in cities around the world, installing infrastructure, physical infrastructure, to facilitate the landings and takeoffs of Uber Air eVTOL, and then ultimately to service the demand in those cities with fleets of these vehicles and simulate them throughout the mission day. So last year, we gave you a glimpse at this, just the very beginning. We showed how through Flux Optimizer, we could take a look of the aggregate multimodal trips within a city, in this case, it's Los Angeles. Take that, understand where clusters of demand are, and actually locate optimal skyport locations. We also shared with you vehicle requirements for Uber Air eVTOL. Things like 150 miles per hour cruise speed, a payload of a pilot and 4 passengers, a sizing range of 60 miles, a noise signature that's on the order of 15 dB less than a helicopter of equivalent weight, as well as all electric, because an all-electric vehicle is on the order of 3.5 times more efficient than a non-electric vehicle. So since then, we've taken Flux Optimizer, we've taken our vehicle tools, and we've combined them together into a framework for us to validate these requirements. And so by combining them, we've essentially built up this framework. And we've talked about Flux Optimizer as though it was the single tool. It's not. It truly is a framework. It's a collection of tools, capabilities, functions, and features that allow us to see and prognosticate the world and the vision that we have for Uber Air. We start with inputs, which include the vehicle, batteries, and network assumptions. And we synthesize these to be able to derive insights and to be able to optimize skyport locations, generate candidate Uber Air trips, and then ultimately simulate the flights of these Uber Air eVTOL to satisfy that demand. Underlying all of that is an economic model which is able to capture the indirect and direct costs, some of which we'll discuss later today, as well as a demand model which helps us capture the price-time trade-offs for Uber Air riders. Let's dive a little bit deeper into these inputs. So we start with a vehicle model. We utilize our internal tools as well as validated industry standards, like NASA's NDARC, to characterize the flight performance of these aircraft, and then distill them into metrics that Flux cares about. Things like lift-to-drag ratio in cruise, or disk loading, or even the max takeoff gross weight as we size these vehicles. We then install a pack. We can utilize cell test data that we're testing in our own labs, and we're talking about in a separate track, to then build up a pack, install it into the vehicle, and then utilize relevant duty cycles for each aircraft so that we understand the impact of that vehicle in the network over the mission day. Combined with that are network assumptions. These essentially tell us how we're going to fly these vehicles. Maybe you've designed a vehicle that can cruise at 175 miles per hour, but you want to operate it on the network at 150 miles per hour. We can vary the payload depending on the trips that we're making, and the skyport nodal locations can be varied and constrained depending on the max range capability of those vehicles. And so with those, we can now instantiate skyport networks of various sizes. Maybe we start with a skyport network at launch that's 6 skyports, or something that's more mature like 13 skyports, or maybe something at scale, 75 skyports, all the while rolling in operational assumptions. Noise, efficiencies, trip wait times, all of this can get rolled up, and we can vary these things in ways that help us understand sensitivities to the network. We can look at how indirectness might change using data from Uber Copter or even additional analyses. And we can also vary how these vehicles are flown or vary the vehicles and the batteries themselves that are in the network simulation. So with all of these inputs, we then go into the actual capabilities of Flux. What you see here is mostly a refresher for those of you that were at last year's summit. Again, we're taking the trip data within Los Angeles, understanding where net trip inflows and outflows are, to then aggregate an understanding of demand, cluster that, and realize where we can place skyports within that network. And we can see how these skyport networks grow over time. Key insight, we make sure that as we grow, it's inclusive of the previous skyport nodes. We can take the total addressable market and resize these skyports, and then ensure that there's enough FADOs and parking pads to satisfy the demand and the trips that we would like Uber Air to service. Over time, we can install more FADOs, more parking pads, to look at how this changes network productivity and ensure that we are matching the growth of our fleet over time. So to tell you a little bit more how we size that fleet and then how we actually simulate that fleet, I'm going to bring onto stage my colleague, Revati.
Hi, everybody. My name is Revati. I'm the product manager for the Elevate Data Science team, the team that brings you Flux Optimizer. Like Ian mentioned, it is really critical for us to be able to determine where to place candidate skyports and how many pads to allocate to each of them. But in a network as complex as an urban aviation system, we need to be able to quantify the impact of any one component on the rest of the network. So we bring back the flywheel that we saw last year, and we realize that as you lower prices, you induce more demand, which then you can capture with a well-utilized fleet. A well-utilized fleet with a high load factor lowers our acquisition and operational costs, which then enables us to continue to lower the price point for Uber Air. As a result of this analysis, we've discovered the two biggest drivers of network impact are the price point of the network and the number of vehicles in the network. And these affect outputs, among others, such as the profitability of the network and the number of riders that we have the capability to serve. Uncovering the relationships between these inputs and outputs is a complex task that involves multiple layers. However, we can use Flux to scan different network configurations so that we can better understand the trade-offs of optimizing a network for throughput or for profitability, or any other business metric, until we understand how to configure our inputs. Once we have correctly configured inputs, we're able to run a mission day in Flux. And I'm going to show you what that looks like today for a 25-node network in LA. In this visualization, trip outflows, or origins, are represented by the blue clusters, and trip inflows, or destinations, are represented by the purple clusters. I'm going to play through this day and stop at critical points in this junction. In the morning, as we can see, the trip outflows are centered around, are present in the surrounding areas around LA, whereas the trip inflows are centered at critical urban centers such as Santa Monica, West Hollywood, Los Angeles, and Santa Monica. As I keep playing through the afternoon, we see that trip flows decrease significantly, but there's still a high inflow of trips going into LAX. As I play through the evening, we can see an inversion of the pattern that we saw earlier, where trip inflows are in the surrounding areas and trip outflows are coming from these major urban centers. And this is a pattern that becomes more and more pronounced as I run the rest of this mission day. Not only is a Flux run fun to watch, it also provides us critical business metrics that we can inspect to confirm existing hypotheses about our network or uncover new relationships that we haven't yet discovered. For example, we see that when we make a rider wait in a terminal, for a longer time, we're actually better able to pool them, which results in a more efficient network overall. Or we're able to quantify the impact of lowering price points on the distribution of a vehicle fleet's utilization. So far, we've been talking about the optimal network, optimal throughput, optimal price point. And all this really requires the optimal vehicle. So how do we define the optimal vehicle? Well, we ran a variety of aircraft specs through Flux to quantify their business impact to the bottom line. I'm going to show you some examples of those differences today. You're looking at here a trip web that represents origins and destinations for a 13 skyport network in LA. Essentially, these are the multimodal trips that we've served in this mission day. It is a flattened version of the visualization that you saw earlier with all the lasers and the colors. What I'm going to show you now is how much fewer of these trips we can serve with a vehicle of 125-mile-hour cruise speed. So we can see that you see lower profits, lower served riders, and overall less network efficiency. Another example, let's lower the payload that this vehicle can carry from 4 passengers to 2 passengers. We see even more pronounced decrease in the number of trips that we can serve and our overall business profitability. And so in this way, we're able to quantify the requirements that we bring to our partners in a way that's backed up by data. Now that I've showed you what Flux is capable of doing on a single run, on a single network configuration, I'm going to bring Ian back on the stage to show you how we can scale. Thank you.
Thank you. So, pulling back from that 13-node Skyport network, we can look at the evolution and the metrics that fall out from the aggregate of these runs. And from this, we're able to see that we can configure these networks to maintain a healthy level of metrics. This is true at every point along the nodal evolution. And so even as we flatten out rider density per Skyport across the market, we can still maintain this. We see that we maintain high load factors higher than 1.5 that some may struggle with. We decrease deadheads, thereby increasing revenue flights, and all the while increase utilization. And so we are able to achieve this, just as Revati said, utilizing vehicles designed to our vehicle requirements. As we scale and we reduce fares, we kickstart our flywheel and see the expected increase in throughput and revenue. And we can configure the technical inputs and network assumptions and the economics of each case on a region-by-region basis. That is what achieving network efficiency is all about. But ultimately, we've got to make it real. We can insert assumptions, we can insert vehicle models, we can insert simulations of the combinations of these things, but ultimately it comes down to real hard effort that we are doing. So my colleagues in the next few talks will tell you a little bit more about our innovative noise modeling, our commitment to safety, how we're driving for community acceptance, and breaking down really what are these eVTOL cost drivers. Thank you.